Introduction. This chapter develops the main components of the battery, starting with its smallest energy unit, the cell, which, grouped together, forms a cell module, and several make up the battery pack. The battery design can be very varied depending on the technology used, such as the number of cells, cell packaging, cell types, cell sizes, cooling, etc. Obtaining the stored energy, power, energy density, etc. in addition to the cost of the battery. Depending on the technology used, the battery will have advantages and disadvantages that must be taken into account when purchasing the vehicle and providing the service, such as the risk of fire, better protection against impacts, overheating, discharge, etc. Index. Battery cell. Cell types. Traditional packaging technology. CTB Cell-to-Pack technology. CTC Cell-to-Chassis. CTB Cell-to-Body. Battery cooling-BTMS. Subscribe to the Fleet Management channel. Your subscription is a great support to continue making new videos. Subscribe. 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 Battery Cell 1. The cell is the smallest unit of electrical energy storage in the battery. Each cell joins its counterparts in series in order to add their voltages and increase the energy storage capacity, which will later be delivered to the electric motor, among other components, and which drives the vehicle. The battery cells of electric vehicles are rechargeable thanks to the fact that their electrochemical reactions are reversible. It must have a high energy density to store the greatest amount of electrical energy possible, and the vehicle has greater autonomy. The voltage of a fully charged lithium-ion cell is between 3.74.2 volts. The nominal voltage of a cell is a function of its anode and cathode materials and its impedance. Each different combination of materials will give us a certain cell potential. This open circuit voltage varies as the cell is charged or discharged. So when we say that a cell has a certain voltage, we are actually talking about its nominal voltage. 100% charged will give more voltage and unloaded less. In lithium batteries, the state of charge of the battery is proportional to the voltage they give in an almost linear way between their maximum and minimum. The battery voltage starts at 4.2 volts, which is the maximum, and begins to drop to 3.7 volts for most of the battery's life. The minimum voltage for lithium batteries is 3.4 volts. At this voltage, the battery is dead. Charging more than 4.2 volts per cell can cause stress on the cell, resulting in oxidation that reduces battery life and capacity, and lower voltages can increase battery charge cycles at the expense of shorter operating time. Stored energy. The capacity of the cell is measured in watt-hours, that is, power per time. If the capacity of a cell in watt-hours is not known, it is often given in the form of milliamp-hours or ampere-hours. Theoretically, if a cell, for example, has a nominal voltage of 3.6 volts and 2000 milliamp-hours, since power is voltage times intensity, then the capacity of that battery is 3.6 volts times 2 amps, 7.2 watts for 1 hour, or 7.2 watt-hours of energy. In practice, it is more complicated because the capacity of a cell changes slightly depending on the intensity at which it is discharged. If we discharge it slowly, we will obtain more energy than if we discharge it quickly. The graph shows the ampere hours on the x-axis, voltage on the y-axis, and various curves have been represented depending on the discharge intensity. For a discharge intensity of 0.2 amperes, 4.5 amperes hours are obtained. For an intensity of 7 amperes, we obtain around 4.15 amperes hours, and for intensities of 10 amperes, we obtain around 2.25 amperes hours. 1 coulomb is also that figure that is usually given to us for a battery in milliamp hours, or sometimes in ampere hours. It is the nominal current, so to speak. In fact, 1 coulomb is supposed to be the current that the battery would have to give for 1 hour to discharge completely. For example, in that 2000 milliamp hours, cellular current of 1 coulomb is 2000 milliamp, and if we say that it works at 0.5 coulomb, we mean that it is being discharged at half the current at 1000 milliamp. It is common to sometimes give the capacity of a cell at a certain discharge rate. A perfect example is the Nissan Leaf, whose 3.8 volt cells claim to have 33.1 ampere hour. So doing the math, the Leaf has 192 cells divided into 48 modules, supplying a final 24 kilowatt hours. But that capacity is as long as they are discharged, constantly at 0.3 coulomb cell power. The power delivered by a cell at a given moment is as simple as multiplying voltage by intensity, but we must also take into account the limitations imposed by the chemistry and internal structure of the cell. Here we fully enter into the issue of the internal resistance of the cell and also into aspects such as the speed of chemical reactions and the capacity for movement of ions. So, as we demand more and more current from the cell, we will eventually reach a point where the chemical reaction decays or does not occur fast enough. It will also get hotter and the cell will probably fail quickly. For example, it happens that there are certain cells that, without having good capacity, are very powerful, such as lead cells, while others with excellent capacity have very low power, such as zinc-air cells. Generally, in the specifications of each cell, we find data on the maximum intensity that it can provide at peak currents in the form of multiples of a coulomb. Continuing with the example of the 2000 mAh cell, if it could provide peak power of 10 coulomb for a few seconds, then it would be able to give us up to 20 amps for a few seconds, so the nominal power of the cell is 7.2 watts and the peak power is 72 watts. Let's take the example of the Tesla Model S. We know that the best pack is 85 kilowatt hours. If each cell works at 1 coulomb, the pack is supposed to have about 85 kilowatts of power. However, the 85 kilowatt hours performance version is capable of delivering up to 310 kilowatts, so at times all the cells that make up its pack work with current peaks of 3.65 coulomb. In fact, the most suffered version is actually the 40 kilowatt hours one, since when we squeeze the 175 kilowatts from its motor, the pack works with current peaks of 4.37 coulomb. However, most of the time when moving without accelerating, the car does not need more than 20 or 25 kilowatts of power, so the battery will usually work at 0.25 coulomb or less.
Learned about our fleet management consulting and training services, reduce costs and optimize fleet management activities. We electrify your fleet of vehicles. We carry out the electrification plan until its implementation, known as
Battery Cell 2. Cell size. The size of the cells is varied. Each vehicle manufacturer uses a size. The larger the cell size for the same components, the greater the energy storage. Cells can be classified as large and small. Large cells. It is the simplest way to manufacture a pack, and it is used by the vast majority of hybrid and electric vehicle manufacturers. At a constructive level, the number of connections and the complexity of all systems, such as battery management system BMS and cooling, is much lower. In the event of a serious failure of one of our cells or modules, the entire pack seriously suffers in power and capacity, or may stop working altogether. The larger and more capable the battery cells used, the less flexible the capacity of our pack is, and the more sensitive it is to failure, but its construction is also simpler and cheaper. Small cells. This type of cells are used due to their great availability, since they are manufactured in millions and have more competitive prices. Also for its higher specific energy and greater ease of cooling thanks to its cylindrical shape factor. The small size of its cells allows great flexibility in the shape of the pack, and reliability also increases. They dissipate heat better, but also complicate cooling systems. Cooling the 200 or 300 cells of most current cars is not the same as the nearly 8,000 of the 85 kilowatt hours Model S. Furthermore, the greater the number of cells, the BMS becomes even more complicated, and of course all this is much more expensive than in a pack made in the other simpler way. Many small cells complicate the aspect of their interconnection, increasing the complexity of the BMS and their cooling, but allows us finer control of capacity and power, and better figures for specific energy and pack density. Cell life is the most critical factor. Any damage to one cell will lead to damage to the entire battery pack. Cell structure. The structure of a lithium-ion cell is as follows. The cells are wound extremely tightly and are confined within a special metal casing that reduces the chances of battery swelling and electrode damage. The negative electrode is basically a very thin sheet of copper. The positive electrode is composed of an ultra-thin sheet of dark-colored lithium alloy that concentrates the charge potential. And the separator consists of a porous plastic polymer that contains the lithium salt that forms the electrolyte. In addition, the separator prevents both positive and negative sheets from touching each other and causing a short circuit. All these elements are packaged in a cylindrical, prismatic or bag structure as developed below. Cell types 1. Currently, there are three main types of cell configurations that stand out among battery manufacturers. The three main geometries are cylindrical, prismatic, and bag type. Each of these geometries influences the thermal dissipation, important in lithium-ion batteries, which above 60 degrees Celsius suffer degradation that produces flammable gases, which, in considerable accumulations, can lead to cell fire. The amount of energy that can be stored in each cell, also known as packing density, the rigidity of its structure, the manufacturing cost, design of cooling systems, final weight and size of the battery system, housing design, prismatic cells. They are characterized by their packaging capacity thanks to their stacked layer configuration. They are a battery geometry that is made up of a series of positive and negative electrodes sandwiched in a rectangular shape. The chemistry of a prismatic cell is enclosed in a rigid casing, mostly made of aluminum or steel, to ensure a high level of stability. Due to this unique architecture, prismatic cells are typically lightweight and thin. There is no predefined format of this type, and each manufacturer opts for a specific size or design that best suits its purpose. Prismatic cells tend to be used in applications that require high energy density, such as energy storage systems and electric vehicles. Pouch cells. They are characterized by their light weight, thanks mainly to the use of aluminum as a material for the coating, although they also stand out for their small size and flexible cells that can easily adapt to almost any space thanks to a packaging efficiency of between 90% and 95%. They also have a higher energy density. This format is very promising for the future since solid-state batteries can work with this type of cells. Cylindrical cells. They are configured with a series of electrodes that are enclosed in a circular geometry. The cells are wound extremely tightly and are confined within a special metal casing, which reduces the chances of battery swelling and electrode damage. Cylindrical cells tend to be small and round, allowing them to stack on top of each other. Generally, cylindrical cells are used in medical devices, electric bicycles and satellites. Cylindrical batteries can be produced much faster and at a lower cost per kilowatt hour than prismatic cells. Their adoption is due to a cost savings issue, since they are cheaper to manufacture. These have become notably popular thanks to their adoption by Tesla. Although cylindrical cells often have a lower capacity than prismatic cells, they have an advantage in terms of power output. Cylindrical battery cells are designed in such a way that if their internal pressure increases too much, they will rupture, meaning they are unlikely to catch fire or explode. There is no format that stands out among the others, but the battery that each manufacturer chooses can affect the design of the final product in many different ways. An example of this is how the cell format can affect, for example, the temperature distribution and heat transfer pattern, also the price of the vehicle on the market, or the distribution of its internal devices, such as the cooling system, or even the location of the electric motor or motors, as well as the aesthetics of the vehicle in question and its dynamic behavior, mainly due to the greater or lesser weight that they cause. Hence, each battery manufacturer is betting on different types, in some cases even combining the development of several in parallel. There is no clear consensus in the industry on what format the future of battery technology may take. The manufacturer LG Chem mainly opts for producing bag-type cells, although it is also producing cylindrical type cells as one of Tesla's suppliers. Samsung, for its part, has a very similar case to the aforementioned brand, since it also supplies cylindrical cells to Tesla but generally prioritizes the use and development of cells in prismatic format, which it supplies to other firms such as Volkswagen. In the count of cell manufacturing corporations, we also find SK Innovation or Farise, which opt for the bag-type format, and supply companies such as Mercedes, Hyundai, Kia or Geely. KTL or Goshen do the same with the prismatic format. Panasonic, Tesla's main supplier, mainly manufactures cylindrical cells. Over the next few years, we will see new formats that complement the existing ones. Cell types 2. Batteries are the ones that are most vulnerable and predisposed to damage, since they are located under the body in the central part of the vehicle and can receive knocks and impacts. Due to this vulnerability, manufacturers generally choose to use cylindrical or prismatic type cells, which have a more robust or resistant gasket, which reduces the risk of suffering considerable damage by making them more resistant to impacts and punctures. When the space for the battery is limited and lightweight is also required, pouch-type cells are used, which are only covered by a polymer and aluminum film.